Since the cell potential depends on the concentration of the half-cell solutions as well as the temperature, we can only compare the cell potentials if we always work at standard conditions. Let's consider a standard zinc copper cell. The potential difference reading will be the standard EMF only if the solutions of the two half cells are 1 mole per cubic decimeter each. Zinc sulfate in this case has a concentration of 1 mole per cubic decimeter, and the copper sulfate solution also has a concentration of 1 mole per cubic decimeter. And the temperature at which we have to work is 298 Kelvin. Those are what we call standard conditions. The standard cell EMF, which is measured at standard conditions, is a quantitative measure of the tendency of the cell reaction, or the overall reaction, to run from left to right. In other words, to produce zinc ions and copper in this case. Chemists are very interested in the abilities of substances to act as oxidizing agents or as reducing agents. The relative strengths as oxidizing or reducing agents could be compared if we could obtain numerical values for the standard half-cell potentials or electrode potentials. But as we mentioned before, one cannot measure the standard electrode potential of a single electrode by itself because we have to have another electrode and a salt bridge to complete the circuit. Fortunately, we can determine the standard electrode potentials and find values in volts for these if we make an arbitrary assumption about the potential of a given standard electrode that we call the hydrogen electrode. This consists of a piece of platinum immersed in an acid solution of concentration 1 mole per cubic decimeter at a temperature of 298 Kelvin, and with a steady current of hydrogen gas at a pressure of 1 atmosphere bubbled over it. The standard electrode potential assigned to this half cell is 0 volts for comparison purposes. Now, this is the symbolic representation of the standard hydrogen electrode, where platinum is in contact with hydrogen gas, which is adsorbed on the surface at a pressure of 1 atmosphere. And this gas, in turn, is in contact with the hydrogen ions of the acid at a concentration of 1 mole per cubic decimeter, because we are working at standard conditions. And the whole half cell is connected via the salt bridge to the other half cell. What do we mean by the standard electrode potential of an element? That will be the potential difference reading or the voltmeter reading obtained when this element is connected to the standard hydrogen electrode, all conditions being standardized. In other words, the half cell concentrations must be 1 mole per cubic decimeter at a temperature of 298 Kelvin. The standard electrode potential is a quantitative measure of the ability of the element to donate electrons as compared to the ability of hydrogen to donate electrons. If we want to compile an activity series of reduction potentials, then we always connect the standard hydrogen electrode on the left. That's by convention. And then, if the potential difference reading is positive for all, like for all these cases, elements and compounds here, that means if the pointer of the center zero voltmeter deflects to the right, or an ordinary voltmeter would show an on-scale reading when the hydrogen electrode is connected to its negative terminal, then it means that hydrogen is a stronger reducing agent than the particular element or compound, and therefore the particular element will occur below hydrogen in the activity series. But if the reading is negative, like for these elements, magnesium, zinc, and iron on our table here, in other words, when the pointer of the center zero voltmeter deflects to the left, then it means that the particular element is a stronger reducing agent than hydrogen, and the electrons will flow from the element half cell to the hydrogen half cell. Let us see how the standard electrode potential of a given standard half cell can be measured. We are going to look at the standard zinc electrode, and according to our convention, we always connect the hydrogen electrode on the left-hand side. That means the standard hydrogen electrode is connected to the negative terminal of the voltmeter, and the other electrode is connected to the positive terminal. In this case, we see that the center zero voltmeter deflects its pointer to the left. And what does that mean? It means electrons flow from the zinc standard half cell via the voltmeter to the hydrogen half cell. What does this mean? It means that zinc is a stronger reducing agent than hydrogen. What does that mean? It means zinc is above hydrogen in the activity series. And here we see the standard electrode potential measured for zinc is minus 0.76 volts. Let us explain to you what happened in this case. The surface atoms of the zinc electrode goes in solution in the form of zinc cations, each leaving 2 electrons behind on the electrode. This is the so-called oxidation-half reaction, where zinc was oxidized because it lost 2 electrons. Together with many more such electrons, mutual repulsion will take place on this electrode, causing an electron current to flow from the standard zinc half cell via the voltmeter to the standard hydrogen electrode. On arrival at this electrode, we get reduction. The reduction half reaction takes place, where the hydrogen ions acted as the oxidizing agent, which was reduced when electrons were added to it to form the hydrogen gas. The overall or cell reaction indicates that zinc was the reducing agent which donated electrons to the hydrogen ions, which was acting as the oxidizing agent to produce zinc ions and hydrogen gas. This here is the symbolic representation of the same cell, where on the left we have the platinum electrode in contact with hydrogen gas at a standard pressure of 1 atmosphere. And this is in contact with the hydrogen ions and the standard concentration conditions. And what is that? 1 mole per cubic decimeter. And that is in contact via the salt bridge with the zinc half cell, which consists of zinc ions at the same standard concentration of 1 mole per cubic decimeter in contact with the zinc rod. We are now going to calculate the standard electrode potential of zinc. This formula gives the cell or standard cell potential, or cell M for any cell, where we always find that the standard electrode potential of the element that we have on the right-hand side in our symbolic representation is written first. That's why we refer to right, the right-hand side, minus the standard electrode potential of the electrode on the left. Now, the standard electrode potential on the right here is zinc, so we have the zinc half cell. And on the left we have hydrogen, so this is the standard electrode potential for hydrogen. The cell potential was measured as minus 0.76 volts. So the value also of the standard electrode potential for hydrogen was arbitrarily chosen as 0. So we can calculate the standard electrode potential for zinc, and that works out to minus 0.76 volts, which means that zinc is a stronger reducing agent than hydrogen. Let us see how the standard electrode potential of a copper standard electrode can be determined. Again, we connect the standard hydrogen electrode on the left, connected to the negative terminal of our voltmeter, and the copper electrode is connected to the positive terminal. In this case, we get a positive reading of 0.34 volts, because the pointer of the center zero voltmeter deflected to the right. This means that copper is a weaker reducing agent than hydrogen, and therefore falls below hydrogen in the series. We see the reading was plus 0.3 volt for the standard electrode potential for copper. Now, what happened in this case? On the platinum electrode or the hydrogen electrode, hydrogen gas was oxidized to hydrogen ions when electrons were given off. And when these electrons arrive at the positive electrode or the cathode, the 2 electrons will be added to the copper cation to produce elementary copper, which deposits on the surface. The overall or cell reaction indicates that hydrogen is the stronger reducing agent, which donated electrons to the copper cations, which acted as the oxidizing agent. Here we have the symbolic representation of the cell with the standard hydrogen electrode on the left and the standard copper electrode on the right. We have the formula here again for the cell potential, or standard cell potential, where right refers to the electrode written on the right in the symbolic representation, and left refers to the hydrogen, which is on the left-hand side of the symbolic representation, with a potential of 0 volts. The value that we measured for the cell M was plus 0.34 volts, so the value of the standard electrode potential for the copper half cell is plus 0.3 volts, meaning that copper is a weaker reducing agent than hydrogen. By the same method, we can measure the standard electrode potential of any half cell. to compile the so-called activity series of electrode potentials or standard redox potentials, of which this is a simplified version. Now that we've laid a firm foundation of basic concepts, we are ready to discuss a few applications of the standard electrode potential series. One of the problems that we have sometimes is to find the standard cell potential of an electrochemical cell. Let us say the problem is that we have to design an electrochemical cell based on this spontaneous reaction here. The first step is to first identify the oxidation half reaction and the reduction half reaction. It is clear that zinc is the reducing agent, having lost 2 electrons to form zinc cations. So that will give us the oxidation half reaction. While the reduction half reaction is as follows, where silver cations acted as the oxidizing agent, which was reduced by addition of electrons to metallic silver. By convention, we always write the negative electrode or anode where oxidation takes place on the left-hand side of the symbolic representation of the cell, and the positive electrode or cathode where reduction takes place on the right-hand side. By means of this formula, we can calculate the standard cell EMF of any electrochemical cell, where right refers to the standard electrode potential of the half cell written on the right in the symbolic representation, and left refers to the standard electrode potential of the half cell written on the left. This means that the reduction half cell, where the oxidizing agent is found, is written over here, and the oxidation half cell with the reducing agent on this side. When we refer to the standard reduction potential series, we find that the standard electrode potential for the silver half cell is plus 0.8 volts, while for the zinc half cell, it is minus 0.76 volts. When we substitute these values in our equation for the silver half cell and for the zinc half cell, we get a reading of plus 1.56 volts for the cell EMF, and this value is positive, and when the cell EMF is positive, it always means that the reaction as written from left to right will be spontaneous. You will note that the standard cell EMF for a combination of any 2 half cells can be determined simply by subtracting the standard electrode potential for the half cell higher in the series, like zinc, minus 0.76 volts, from the standard electrode potential of the half cell lower down in the series, like silver in this case, plus 0.80 volts, which amounts to changing the sign of the standard electrode potential higher in the series and then add it to the value of the standard electrode potential lower down in the series. In principle, we can design any cell based on any type of reaction. And let's look at a more advanced example. Let's say we have to design a cell based on this spontaneous reaction over here. And we also have to find the cell EMF. The first step is always to analyze this cell reaction into its oxidation half reaction and its reduction half reaction. We see here that the iron 2 ions have been oxidized by each losing 1 electron to form iron 3 ions. So this is our oxidation half reaction. The reduction half reaction is as follows. The permanganate ions were reduced when electrons were added to them to form manganese ions. We may seem to have a problem in this case because there are no metal electrodes that can take electrons away or from the cell. Because we see in the oxidation half reaction, there is no metal here that's been oxidized to its corresponding cations. And in the reduction half reaction, we don't have metallic ions being reduced to the corresponding metal. But this problem is solved as follows. We set up half cells containing mixtures of the ions involved in each half cell. We get iron 2 ions, for example, from iron sulfate, and iron 3 ions from iron 3 sulfate, dissolved in water to give us the oxidation half cell. And we use a mixture of permanganate ions obtained from potassium permanganate and manganese ions obtained from something like manganese sulfate dissolved in water to give us the reduction half cell, you see. And how do we conduct the electrons away into the cell now? We make use of platinum electrodes. We dip a platinum electrode in this cell to remove the electrons, and we dip a platinum electrode in this half cell to supply electrons. So in this case, the cell will be as follows. The negative electrode or anode where oxidation takes place is platinum dipped in a solution of iron 2 and iron 3 ions connected to a salt bridge, and this is in contact with a platinum electrode, which is our cathode or positive electrode containing permanganate and manganese 2 ions. We can again calculate the cell EMF by using this standard formula, where right refers to the half cell written on the right-hand side of the symbolic representation, which is of course the permanganate manganese half cell, and subtract from that the standard electrode potential of what is written on the left, which is our oxidation half cell consisting of iron 2 and iron 3 ions. If we now go and we look at our standard electrode potential series, we find that the standard electrode potential for the permanganate manganese half cell is plus 1,52 volts, while the value for the iron 3 iron 2 half cell is plus 0,77 volts. Substituting these values in our equation for the reduction half cell, 1,52 volts, and for the oxidation half cell, 0,77 volts, we get a positive value of 0,75 volts. And what does that mean? If it's positive, we know that the reaction, as written from left to right, is spontaneous. A second use of the standard electrode potential series is to predict in which direction a redox reaction will take place or not. In other words, whether the reaction will take place spontaneously, as written from left to right, or not. Our first problem is to determine whether a spontaneous reaction will take place or not when a strip of zinc is dipped in a copper sulfate solution. Now, there are two ways of solving this problem. In the first method, we design a cell which is based on the equation under question, and then we determine the cell potential. If the cell potential is positive, then the reaction will take place spontaneously as written from left to right. But if the cell potential is negative, the reverse reaction actually takes place as written from right to left. Now, if the reaction did take place in this case, the cell reaction would be as follows. Zinc would displace copper ions from the solution, and zinc ions will form, and copper would be deposited if it did take place. And the two half reactions would be as follows. The oxidation half reaction would be zinc oxidized to zinc ions, losing 2 electrons, and the copper cations will undergo reduction in the reduction half reaction when electrons are added to form elementary copper. And the cell would be the zinc half cell on the left, because we always write the anode or the negative electrode where oxidation takes place on the left, and the copper half cell where reduction takes place on the right. Again, we can calculate the cell EMF using this formula, where right refers to the half cell on the right of the symbolic representation, the copper half cell, and left refers to the zinc half cell written on the left. If we now look at our standard reduction potentials, we find that the standard electrode potential for the copper half cell is plus 0,34 volts, and for the zinc half cell, it is minus 0,76 volts. If we now go and substitute these values for the copper half cell and for the zinc half cell and do our calculation, we get a positive reading of 1,1 volt for the cell EMF. Because the cell EMF is positive, the reaction is spontaneous as written from left to right. A second method is to simply write down the half reactions in the order in which they are listed on the activity series. We see that zinc is a stronger reducing agent than copper because it's above copper in the series. So it means that the reverse reaction takes place for the zinc half cell because electrons are being donated by the zinc. And if this half cell is now connected to the copper half cell, the forward reaction will take place for the copper half cell because electrons are being added to the copper ions. A simple rule to remember is that we can always simply connect the two half reactions by a counterclockwise arrow to find out in which direction the spontaneous reaction will occur. And so in this case, the reaction is spontaneous as written from left to right. What would happen if we do the opposite, if we place the copper strip in a zinc sulfate solution? In this case, we get no reaction. If the reaction did take place, then what would your cell reaction look like? It would be the following. Copper would displace zinc ions from solution, if it could, to form copper cations, and zinc would be deposited. The half reactions would be as follows. The oxidation half reaction would take place with copper being oxidized to copper ions, and the zinc ions would have been reduced, if it did take place, by adding electrons to form solid zinc. And the cell reaction would be as follows. We'll have our copper half cell, the oxidation half cell, as usually written on the left, and the zinc half cell, as usual, written on the right. And the cell EMF would be calculated as follows, where right refers to the zinc half cell on the right here, and left refers to the copper half cell, which we have on the left. If we now refer to the standard electrode potentials, we find that the electrode potential for the zinc half cell is minus 0.76 volts, while the standard electrode potential for the copper half cell is plus 0.34 volts. Substituting these values in our equation for the zinc half cell, minus 0.76 volts, and for the copper half cell, plus 0.34 volts, we find a negative answer for the cell EMF of 1.1 volts. Because the cell EMF is negative, we have no reaction as written from left to right. In our second method, we once again write the two half reactions in the order in which they are listed on the table. But because zinc is above copper in the table, zinc will be a stronger reducing agent. And if we join the two half reactions counterclockwise, we see that the reverse reaction is the actual one that takes place in this case. So the forward reaction, as written, will not take place.